At 0847 hours on March 6, 1944, Technical Sergeant Robert Dutch Vandermeer stood on the frozen hardstand at Debden Airfield, England, watching 48 P-51 Mustangs taxi toward the active runway. The morning air smelled like aviation gasoline and exhaust smoke. Frost covered the wings. The Merlin engines made a sound Vandermeer knew intimately after 11 months of maintenance work. A deep, throaty roar at 1,200 revolutions per minute, smooth and powerful. His hands still smelled like fuel from the night before. 3 hours of work in a cold hangar. One fuel control unit disassembled, modified, reassembled. One 0.02-inch steel shim installed, where regulations said nothing should be installed. One illegal modification that could either save a pilot's life or end Vandermeer's career. Captain James Halford's P-51 was third in the taxi sequence. Serial number 43 to 6315. Named Dallas Blonde in yellow script below the canopy. The aircraft Vandermeer had worked on last night while everyone else slept. The aircraft carrying his unauthorized modification into combat for the first time. Mission parameters: Berlin, 600 miles into Germany, 8-hour round trip. 25,000 feet altitude. The coldest, thinnest air these Packard Merlin engines would ever breathe. The altitude where engines quit and pilots died. 47 P-51 seconds had factory-standard fuel control units. One had Vandermeer's modification. If it failed, Halford would bail out over Germany or crash. If it failed, Vandermeer would face court-martial for sabotaging military equipment. Dishonorable discharge. Federal prison time. If it worked, it could save every pilot in the 4th Fighter Group. Vandermeer watched the P-51 seconds roll down the taxiway. Watched them turn onto the runway. Watched Halford's fighter lift off at 0852 hours and climb toward the morning sun. Then there was nothing to do except wait and hope his calculations were correct. The problem had been killing pilots for 3 weeks. Between March 4th and March 28th, 1944, the 8th Air Force lost 22 P-51 Mustangs to engine failure over Germany, not to flak, not to Messerschmitt fighters, to mechanical failure at altitude. 22 aircraft, 22 pilots, 0 combat losses, pure equipment failure. The pattern was consistent. Every pilot reported the same sequence. Smooth operation at 22,000 feet. Rough running at 24,000. Detonation and engine seizure at 25,000. The timing varied by minutes, but the outcome never changed. The engine quit, deep inside enemy territory, no friendly airfields, no glide path home. Lieutenant David Morrison, March 8th. Engine seized near Hanover at 24,500 feet. Morrison bailed out at 18,000 feet. Parachute deployed normally. Wehrmacht troops captured him 3 hours later. Prisoner of war. 23 years old. Ohio. Captain Robert Chen, March 12th. Engine detonated over Brunswick at 25,000 feet. Chen attempted a forced landing in occupied territory. Aircraft crashed short of a farm field. Chen died on impact. The Germans buried him in a local cemetery. His family received notification 2 weeks later. Lieutenant William Hayes, March 15th. Engine exploded over Magdeburg at 26,000 feet. Hayes bailed out successfully, captured by German police in a small town, sent to Stalag Luft III. He'd sit out the rest of the war behind wire. Recovery rate: 0 aircraft, 0 engines. Deep penetration missions meant no friendly territory for emergency landings. When the engine quit over Germany, the pilot had 2 choices: bail out and become a prisoner, or crash and die. The psychological impact was worse than the casualties. Every pilot flying Berlin missions heard the stories. Heard how Morrison's engine had sounded rough for 90 seconds before it seized. Heard how Chen had radioed engines going 30 seconds before the crash. Heard how Hayes had screamed over the radio when his engine exploded. Every pilot knew the odds. Knew that climbing to 25,000 feet meant risking engine failure. The sound of rough running became the sound of death. The moment when the engine note changed from smooth to ragged. When combustion went from controlled to chaotic. When detonation started destroying pistons, pilots kept flying anyway. The mission required it. The engine was a Packard Merlin V-1650-3, licensed copy of the British Rolls-Royce Merlin. Specifications: 1,695 horsepower, V12 configuration, liquid-cooled, supercharged, reliable at normal altitude, lethal above 23,000 feet. The automatic mixture control system was supposed to solve the altitude problem. The system used a barometric capsule to sense altitude via air pressure. As the aircraft climbed, air pressure decreased. The capsule's aneroid diaphragm compressed. Compression moved a linkage that adjusted fuel flow. More altitude meant richer mixture, more fuel to compensate for thinner air. The system was designed to maintain optimal 14:7 air-to-fuel ratio from sea level to 25,000 feet. At normal altitude up to 20,000 feet, it worked perfectly. The barometric capsule sensed pressure changes. The diaphragm moved smoothly through its adjustment range. Fuel flow increased proportionally. Combustion remained optimal. Engines ran cool and smooth. Above 23,000 feet, the system failed. The barometric capsule reached maximum compression. The spring providing adjustment tension bottomed out. No further adjustment was possible. But the aircraft kept climbing. Air kept getting thinner. Fuel flow stayed constant while air volume increased. The mixture went lean. Too much air, not enough fuel. Lean mixture consequences were catastrophic. Combustion temperature increased 150 degrees Celsius. Piston crowns overheated. The fuel-air mixture ignited before the spark plug fired pre-ignition. Uncontrolled detonation followed. Shock waves hammered the pistons. Cylinder heads cracked under thermal stress. Engine failure occurred within 90 seconds of detonation onset. Engineering Command's official response: operate at 22,000 feet maximum altitude. The order created an impossible strategic problem. B-17 Flying Fortress bombers cruised at 25,000 feet. Fighter escorts at 22,000 feet flew 3,000 feet below the bombers they were supposed to protect. Fighter escort below the bomber formation was tactically useless. The entire strategic bombing campaign was compromised by the altitude gap. German Luftwaffe pilots exploited it immediately. Messerschmitt Bf. 109 seconds dove through the escort altitude, attacked bombers from above. P-51 pilots couldn't intercept without climbing into the failure zone. Climb to protect the bombers and risk engine failure. Stay low and watch B-17 seconds get shot down, the impossible choice. Follow doctrine and abandon the bombers. Break doctrine and die when the engine quit. Vandermeer knew that regulations said operate at 22,000 feet. Knew the engineers said the mixture control system was adequate. New command said the problem was pilot error or bad luck. But Vandermeer also knew 22 dead pilots in 3 weeks wasn't bad luck. It was a design flaw. And he'd spent last night fixing it with a piece of steel the thickness of 5 sheets of paper. Now Halford was flying toward Berlin with that fix installed in his engine. Either it worked and pilots stopped dying, or it failed and Vandermeer's military career ended in a court-martial. There was nothing to do now except wait. Technical Sergeant Robert Dutch Vandermeer was 28 years old in March 1944, Detroit, Michigan. Pre-war, he'd worked as an automotive mechanic specializing in high-performance engines. Good with his hands, better with numbers. The kind of mechanic who understood not just how engines worked, but why they worked. He'd spent 3 years at Packard Motorcar Company, 1938 through 1941. Started as a floor mechanic. Promoted to engine specialist after 6 months. Worked on Packard V-12 marine engines, big, powerful, temperamental. Learned to diagnose problems other mechanics missed. Learned that specifications on paper didn't always match reality in the field. December 7th, 1941, changed everything. Pearl Harbor. Vandermeer had 3 friends who worked at the naval yard there. All 3 died when the Japanese bombed the harbor. Vandermeer enlisted the next morning. December 8th. Didn't wait for the draft. Didn't think about it. Just knew he couldn't sit in Detroit working on car engines while the country was at war. The Army Air Force sent him to Chanute Field, Illinois, for mechanic training. 6 months of intensive instruction. Airframe systems, power plant maintenance, hydraulics, electrical. Vandermeer graduated in the top 5% of his class. Not because he was smarter than the other mechanics, because he paid attention to details other people ignored. Advanced training followed. 6 weeks at the Packard Merlin engine specialist course. The Merlin was different from anything Vandermeer had worked on before. British design, American production, liquid-cooled V12, supercharged, capable of extreme altitude performance, complex fuel system, sensitive to maintenance procedures, unforgiving of mistakes. First posting, 31st Fighter Group, North Africa, August 1942. Spitfire Mark verses with Merlin 45 engines. 6 months in the desert maintaining fighters in conditions that destroyed engines faster than combat did. Sand in everything. Heat that warped cylinder heads. Dust that clogged fuel lines. Vandermeer learned to maintain Merlins in the worst possible environment. Transfer to England, 4th Fighter Group, Debden Airfield, June 1943. P-51 Mustangs with Packard Merlin V-1650 engines. Better conditions than North Africa, but harder missions, deeper penetrations into Germany, higher altitudes, longer flight times, more stress on engines. By March 1944, Vandermeer had been at Debden 9 months, 47 Merlin engines maintained, 2,100 flight hours logged in maintenance records. He knew these engines better than anyone else in the fighter group, knew their sounds, knew their weaknesses, knew when something was wrong before the gauges showed problems. His reputation among pilots, thorough, methodical, perfectionistic. He never signed off incomplete work, even when officers pressured him to rush inspections. Never cleared an aircraft for flight unless he was certain it was safe. Other mechanics consulted him on difficult problems. Crew chiefs asked his opinion when something didn't look right. But Vandermeer saw patterns engineering command ignored. He kept detailed personal notes on engine failures, logged every detonation incident, recorded every pilot report of rough running at altitude, built a statistical model in a notebook. Failure rate correlated directly with altitude. Above 23,000 feet, failure rates spiked. Below 20,000 feet, failures were rare. He'd shown the data to engineering officers. They dismissed it. Anecdotal data, not rigorous testing. They believed Packard's specifications, believed the factory testing, believed the design was adequate. Vandermeer believed the pilots who kept dying. February 20th, 1944. Lieutenant Thomas Parker's aircraft, P-51 NA, serial number 43 to 6819. Parker was 25 years old, Oregon. Quiet kid, competent pilot, 23 combat missions without incident. Vandermeer conducted the pre-flight inspection at 0630 hours, everything within specifications. Compression test. All 12 cylinders between 155 and 160 pounds per square inches. Perfect. Oil pressure. 70 pounds per square inches at idle, 85 pounds per square inches at full power. Normal. Fuel pressure. 14 pounds per square inches, steady, no fluctuation. Mixture control. Full travel, smooth operation, no binding. Magneto timing. Perfect on both systems, no drop on either mag check. Vandermeer signed off the aircraft at 0745 hours. No. Reservations. The engine was perfect according to every standard the Army Air Force used. Parker took off at 0815 hours. Mission, bomber escort to Leipzig, 520 miles into Germany. 7-hour round trip. Altitude, 25,000 feet. Radio call came at 1140 hours. Parker's voice. Red 3 experiencing rough running at altitude. Standard report. Happened frequently. Most pilots dealt with it, completed the mission, brought the aircraft home. Parker continued the mission for 40 minutes on a rough engine. Professional. Disciplined. Stayed with the bomber formation through the target run. Other pilots would have aborted. Parker pressed on. Return flight required climbing to 26,000 feet one more time to maintain position with the formation. At 1,320 hours, pilots heard a loud detonation over the radio. Parker's engine had catastrophically failed. Sudden, complete power loss. Parker feathered the propeller, started a glide toward Belgium, called over. The radio. Red 3 going down, engines gone. He made it to Allied-held territory. Barely. Crash landed at a forward airstrip near Antwerp. Aircraft total loss. But Parker survived. Returned to Debden at 1,420 hours via transport aircraft. Vandermeer inspected the failed engine the next morning, February 21st, cold hangar. Failed Merlin on a maintenance stand. The damage told a clear story. Cylinder number 9 was completely destroyed. Piston crown melted. A hole burned through the top from detonation heat. Cylinder walls showed deep scoring and scuffing. The valves were burned, warped from extreme temperature, head gasket blown, total compression loss, classic detonation damage pattern, textbook example. Vandermeer had seen it before in training, but this was the first time he'd seen it from an engine he'd personally cleared for flight that morning. He pulled the fuel control unit, inspected it thoroughly. The barometric capsule was maxed out at full lean position. At 26,000 feet, the capsule couldn't adjust further. The spring providing tension for the aneroid diaphragm had bottomed out. No more adjustment range. The mixture had gone lean. Combustion temperature had spiked. Detonation had destroyed the engine in under 2 minutes. Vandermeer wrote a detailed report. 4 pages. Included measurements, observations, analysis. Submitted it to the engineering officer, Captain Harold Stevens, 32 years old, MIT graduate, smart guy, good engineer, but he'd never maintained an engine in the field. Stevens reviewed the report. His response? Fuel control unit is within factory specifications. No defect found in mixture control system. Packard design tolerances are adequate for rated altitude. Vandermeer pushed back. Sir, specifications are wrong for operational altitude. The capsule can't adjust above 23,000 feet. Stevens, Packard engineers designed this system to precise standards. They tested it extensively. Vandermeer, Packard engineers don't fly combat missions at 26,000 feet over Germany. Stevens looked at Vandermeer coldly. You're a mechanic, Sergeant. Sign off the inspection report. Vandermeer signed it. No choice. But he knew the problem would kill more pilots. 6 days later, February 26th, Parker flew again. Different aircraft. Same mission profile. Same altitude. Engine failed at 25,000 feet over Brunswick. Parker bailed out, captured by Germans. Vandermeer learned about it at evening mess. Heard pilots talking. Heard them say Parker's engine had quit just like the last time. Heard them wonder if Parker was cursed or unlucky. Parker wasn't cursed. The fuel control system was defective. That night, Vandermeer decided regulations weren't worth another pilot's life. Night of February 26th, 1944. Maintenance hangar, Debden Airfield. 2,240 hours. Most of the crew had gone to barracks. Vandermeer was alone. He pulled a fuel control unit from a scrapped P-51 aircraft. It had been written off after a landing accident 2 weeks earlier. Engine salvageable, parts salvageable. Vandermeer pulled the fuel control unit and carried it to his workbench. Clean white cloth. Tools organized by size. Good light. He disassembled the unit completely. 47 individual parts. Springs, diaphragms, linkages, housings, screws, washers. He laid them out in sequence on the bench. Organization mattered. Lose one small part and the entire unit was useless. The critical component, barometric capsule. Brass construction, 2.5 inches in diameter. Spring-loaded aneroid diaphragm. Function, sense atmospheric pressure. Adjust fuel flow via mechanical linkage. Factory specifications said operational range was sea level to 25,000 feet. Spring tension calibrated for standard atmospheric pressure curve. Maximum diaphragm travel, 6 mm. Vandermeer measured it with precision tools. Used a vacuum hand pump to simulate altitude. At simulated 25,000 feet, the diaphragm reached maximum travel. No further adjustment possible. Above 23,000 feet actual altitude, the spring bottomed out, maxed out, done. He measured the spring rate, 4.2 pounds per inch of compression. Measured the spring preload, the initial tension when installed. Insufficient for extreme altitude compensation. The mathematics worked out on paper. At 26,000 feet, atmospheric pressure dropped to 5.4 pounds per square inches. The capsule required an additional 0.8 pounds per square inches equivalent in spring force to maintain proper fuel flow adjustment. Current spring couldn't provide that force. It was already fully compressed. Result: mixture control stuck at lean. Engine ran hot. Detonation destroyed pistons. The solution was mechanically simple. Increase spring preload. Add initial tension. More preload meant more adjustment range at high altitude. Method: install a shim between the spring and housing. Compress the spring slightly more than factory specification. But the calculation was critical. Too thin a shim. No effect. Problem unsolved. Too thick. Over-rich mixture at low altitude. Potential engine fire. Vandermeer calculated required spring compression, 0.02 inches, 20,000ths of an inch. The thickness of 5 sheets of paper. That additional preload would provide 0.084 pounds additional spring force, sufficient for proper mixture enrichment at 26,000 feet, not excessive at lower altitudes. He found steel stock in the scrap bin, 0.02 inch thickness. Cut a circular shim using tin snips, 1.5 inches in diameter. Deburred the edges with a file. Smooth. No sharp points that could interfere with operation. Fabrication time, 18 minutes. He installed the shim in the control unit, positioned it between the spring seat and housing, reassembled all 47 components, torqued each fastener to specification. Checked clearances. Tested operation by hand. The mixture control moved smoothly, through full range. Reassembly time, 25 minutes. Total modification time, 43 minutes. Vandermeer tested the modified unit by hand, pulled on the linkage, felt the resistance. The spring now had more initial tension, more force available for altitude adjustment. The modification was complete. Nobody knew, nobody approved, nobody authorized. He'd just violated Army Air Force Technical Order 00253. Section 4. Paragraph 12. No field modifications to fuel system components without written authorization from Engineering Command. Penalty for violation, court-martial, dishonorable discharge. Federal prison time for sabotaging military equipment during wartime. But pilots kept dying with authorized equipment. March 5th, 1944. Evening, 1,840 hours. Vandermeer approached Captain James Halford in the mess hall. Halford was 29 years old, Dallas, Texas, pre-war commercial pilot and flight instructor. Combat record: 38 missions, 7 confirmed kills, 6 Messerschmitt BF 109 seconds, 1 Focke-Wulf 190. Calm temperament. Analytical. Trusted his crew chief. Vandermeer asked to speak privately. They walked to the dispersal area. Away from other personnel, cold evening, clear sky. Vandermeer explained everything: the altitude problem, the lean mixture, the detonation pattern. His modification, One 0.02-inch shim installed in the fuel control unit to increase spring preload. The theory: richer mixture at altitude prevents detonation. The risks: unauthorized modification, possible engine fire, possible explosion. Halford listened without interrupting, asked technical questions. How did you calculate the shim thickness? Vandermeer: spring rate times compression distance equals additional force. I need 0.0 minus 8 minus 4 pounds force at 26,000 feet. 20 thousandths compression provides that. Halford: what's the failure mode if you're wrong? Vandermeer: over-rich mixture causes high exhaust gas temperature. You'd see it on the gauge. Engine fire possible. You'd have time to shut down and bail out before catastrophic failure. Halford: can you revert to standard unit if needed? Vandermeer: 15 minutes to swap units. Halford was silent. 30 seconds. Thinking. Vandermeer: same as Parker. Engine quits at 24,000 feet over Germany. You bail out or crash. Either way, you're done. And if the modification fails? Vandermeer: you see temperature rise on gauge, shut down before fire, bail out. Survival likely. Halford: certain failure at altitude versus possible fire with warning. Vandermeer: yes, sir. Halford looked at the P-51 seconds parked on hardstands. His aircraft was there, serial 43 to 6315. Dallas blonde, painted in yellow below the canopy. 214 combat hours. Halford: you confident this works? Vandermeer: I've run the calculations 3 times. Checked spring rates twice. Measured the shim with a micrometer. It'll work. Halford: install it tonight. I'm flying Berlin tomorrow. March 5th, 230 hours. Vandermeer began installation on Halford's P-51. Hardstand number 7. Work lights illuminating the aircraft. Temperature 38 degrees Fahrenheit. Cold night. His breath visible in the work light. He removed the engine cowling panels. 8 Zeus fasteners each side. Accessed the fuel system on the left side of the Merlin. Disconnected fuel lines carefully. Gasoline smell immediate and strong. Unbolted the factory fuel control unit. 4 AN6 bolts, safety wired. Removal time: 19 minutes. Installed the modified control unit. Alignment critical. Gaskets had to seal perfectly. Installation time: 12 minutes. Safety wired all connections. 0.032-inch stainless steel wire. Proper pigtails. Correct tension. Time: 8 minutes. Function check. Manually operated the mixture control. Verified full travel, smooth operation. Time: 4 minutes. Reinstalled cowling panels. Tight fit. Careful alignment of Zeus fasteners. Time: 15 minutes. Final torque check on all fasteners. 5 minutes. Total installation time: 63 minutes. Vandermeer's hands were shaking as he torqued the final bolt. 1 modified engine among 48 aircraft preparing for tomorrow's Berlin mission. He cleaned his tools, wiped gasoline from his hands, walked back to barracks, 0041 hours, lay in his bunk, couldn't sleep, watched the ceiling, counted rivets in the Nissan hut roof, listened to other mechanics snoring, waited for 0500 reveille. Tomorrow would prove whether his calculations were correct or whether he'd just killed a pilot. March 6th, 1944. 0500 hours. Reveille. Vandermeer hadn't slept. He'd been awake counting ceiling rivets for 5 hours. 0530 hours. Breakfast in the mess hall. Toast and coffee. He couldn't eat. Coffee tasted like metal. 0615 hours. Mission briefing. Target, Berlin. 600 miles into Germany. 8-hour round trip. Expected altitude, 26,000 feet over target. Expected opposition. Heavy flak, 100 plus German fighters. 48 P-51 Mustangs from the 4th Fighter Group assigned as bomber escort. 0715 hours. Pilots walked to their aircraft. Halford met Vandermeer at hardstand 7. Pre-flight inspection together. Walk around. Control surfaces. Fuel load. 269 gallons internal. 2 75-gallon drop tanks. Ammunition. 1,260 rounds, 50 caliber, 6 guns. Engine check. Oil level full, coolant topped off, fuel pressure normal. Vandermeer inspected the fuel control unit one more time. No leaks. All connections tight. Safety wire intact. Everything looked correct. No way to know if it worked until high altitude. 0810 hours. Halford climbed into the cockpit. Strapped in. Started the engine. Battery on. Fuel boost pump on. Mixture control to auto-rich. Vandermeer's modification was now active. Magnetos both on. Starter engaged. The Merlin caught on the second blade. Smooth start. Idle at 1,200 RPM. Oil pressure 65 psi. All temperatures normal. To Vandermeer's ear, the engine sounded exactly like every other Merlin on the flight line. 48 fighters running up. Impossible to tell which one carried the modification. 0842 hours. Taxi sequence began. Flights of 4. Halford in second flight, number 3 position. 0849 hours. Second flight cleared for takeoff. 30-second intervals between aircraft. Halford advanced throttle. 61 inches manifold pressure. 3,000 revolutions per minute. The P-51 rolled. Tail came up at 40 miles per hour, rotation at 90, 0852 hours. Airborne. Gear retracted, flaps up. Climb to altitude at 165 miles per hour indicated. Vandermeer stood on the flight line watching. Could track the aircraft for 3 minutes before they disappeared into morning haze. Then nothing. He returned to the maintenance hangar. Tried to work on other aircraft. Couldn't concentrate. Expected time over target, 1,145 hours. Expected return, 1,630 hours. 6 hours, 43 minutes of waiting. Halford's formation joined over the English coast at 0910 hours. Course, 095 degrees. Destination, Berlin. Climb continued. 15,000 feet over the North Sea. 0925 hours. 20,000 feet. Engine running normally. Temperature gauges. 95 degrees Celsius coolant, 85 degrees oil. Normal range. Manifold pressure 46 inches at cruise power. Mixture control in auto-rich position. Working as designed. 0935 hours. 24,000 feet. The critical altitude where problems started. Halford listened to the engine carefully. Concentrated on sound and vibration. Radio calls started coming in. Red 2, running rough at altitude. Another voice. Blue 4, oil temperature climbing. Halford checked his own gauges. Engine smooth. No roughness, no vibration. Temperature gauges still normal. 98 degrees coolant, 87 degrees oil. This was different from every other high-altitude mission he'd flown. Usually by 24,000 feet, he heard slight roughness. Felt vibration through the airframe. Watched temperature needles climb toward redline. Today, nothing. Engine running like it was at 10,000 feet. 0945 hours. 26,000 feet. Level cruise altitude. Halford scanned all gauges, systematically. Coolant temperature, 100 degrees Celsius. Normal range was 95 to 1 to 10. Oil temperature, 90 degrees. Normal range was 85 to 95. Oil pressure, 85 psi. Perfect. Fuel pressure, 14 psi. Perfect. Manifold pressure, 46 inches. Correct for altitude. The modification was working. Engine running cooler than normal at extreme altitude. Richer mixture meant cooler combustion. Cooler combustion meant no detonation risk. 1,015 hours. Dutch coast. Entering German airspace. Radio call. White 3 experiencing rough running, aborting mission. Another call, Blue 2, oil temperature redline, returning to base. 2P, 51 seconds turning, back with engine problems. Standard engines failing at altitude. Halford's engine, perfect operation. 1,055 hours. German border, flak started. 88 mm. Black puffs at 26,000 feet. Formation tightened, 1,130 hours. Link up with B-17 formations, 46p 51 seconds escorting 240 bombers. German fighters appeared, 30-plus Messerschmitts and Fokker Wolfs, 1,145 hours. Berlin, heavy flak, intense fighter combat. Halford engaged 1 Bf-109, no kill. Fighter escaped in clouds. Through the entire target run, his Merlin ran like it was at sea level. No roughness, no overheating, no warning signs. Power consistent, engine responsive. Other pilots were fighting rough engines and German fighters simultaneously. Halford fought only German fighters. His engine wasn't a concern. 1,210 hours. Bombers dropped ordnance. Turned for home. Return flight. 4 hours at 26,000 feet. Engine never missed, never showed stress. 1,620 hours. English coast. 1,647 hours. Debden, tower in sight. Halford entered the traffic pattern. Gear down, flaps down, smooth landing. He taxied to hardstand 7. Vandermeer was waiting. Had been there for 30 minutes. Engine shut down. Mixture to idle cut off. Magnetos off. Silence. Halford climbed out. Flight suit soaked with sweat. 8 hours in an unpressurized cockpit at -40 degrees. He walked to Vandermeer. 2 words. It worked. Vandermeer conducted the post-flight inspection immediately. Halford stood beside him, still in his flight suit, watching. Any problems? Any roughness? Vandermeer asked. 8 hours at 26,000 feet. Engine ran perfect the entire time. Smoother than any high-altitude mission I've ever flown. Temperatures normal throughout. No detonation, no roughness, nothing. Vandermeer pulled the spark plugs. All 12. Inspected the color, light gray. Perfect combustion temperature. No white deposits indicating lean mixture. No black carbon indicating rich mixture. Perfect. He checked cylinder head temperatures using temperature indicating crayons on the exhaust ports. Even temps across all cylinders. No hot spots. Oil analysis. Clean, no metal contamination in the filter. Normal consumption. The engine had performed flawlessly for 8 hours at extreme altitude. Meanwhile, other aircraft from the same mission told a different story. 3 had aborted with engine trouble over the North Sea. Never made it to Germany. Lieutenant Robert Watkins suffered complete engine failure over Belgium, bailed out at 19,000 feet. Wehrmacht captured him 3 hours later. 2 others landed with rough-running engines. Post-flight inspection found cylinder damage from detonation. Halford's aircraft, 0 issues. By 1800 hours evening, mess word had spread through the entire fighter group. Pilots talked quietly at tables. The modification worked. Halford's engine had run perfectly while standard engines failed. March 7th, 0730 hours. Morning briefing for the Crescifing, next day's mission. After it ended, 6 pilots approached Vandermeer in the hallway. Lieutenant Robert Morrison stepped forward first. 24 years old. Ohio. 19 combat missions. Halford told me about the fuel control modification. I want it. Vandermeer explained the risks clearly. No official approval, no engineering testing, violation of technical orders, potential court-martial for both pilot and mechanic, possible engine fire if the modification failed. Each pilot had to acknowledge the risks in writing. Morrison. Watkins bailed out yesterday with a standard engine. I'll take my chances with your modification. Captain Frank Mitchell was next. Flight commander. 31 missions. 8 kills. I watched Halford's engine performance yesterday. Whatever you did, do it to mine. 4 more pilots requested it that morning. Vandermeer met with each pilot individually, explained the technical details. The 0.02-inch shim, the increased spring preload, the theory, the risks. Each pilot signed an informal acknowledgement, not official documentation, just Vandermeer's protection. March 7th and 8th. Vandermeer modified 6 fuel control units. Worked nights after regular maintenance duties. Each modification took 43 minutes. He'd refined the process. Cut shims from steel stock. Measured each with a micrometer. Tolerance, plus or minus 0.001 inch. No variations. Every modification identical. He installed each unit personally. Didn't delegate. Quality control mattered too much. March 9th mission. 8 aircraft with modified units flew Berlin escort. All 8 performed flawlessly at 26,000 feet. 40 unmodified aircraft. 2 engine failures. 1 abort. Lieutenant Hayes bailed out over Germany. The statistics became impossible to ignore. Modified engines. 0% failure rate. 64 flight hours. 0 failures. Standard engines. 4.2% failure rate. 3 failures in 320 flight hours. Pilots started refusing to fly, without the modification. Squadron commanders noticed but said nothing officially. Unspoken policy developed. Don't ask about modifications. Don't document them. Don't report them to command. March 10th. Other crew chiefs started asking questions. Sergeant Carl Rodriguez, crew chief for Mitchell's aircraft, approached Vandermeer in the maintenance hangar. "Dutch, Mitchell's engine ran great yesterday. What you do?" Vandermeer explained the modification. Technical detail, procedure, risks. Rodriguez. "Can you show me how?" Vandermeer taught him. How to disassemble the fuel control unit. 47 components in sequence. How to fabricate the shim. 0.02-inch thickness. Deburred edges. How to install it. Positioning between spring seat and housing. How to test operation after reassembly. Rodriguez completed his first modification in 52 minutes. Slower than Vandermeer, but correct. Vandermeer inspected it before installation. Approved. Sergeant Thomas Bailey learned from Rodriguez. Knowledge spreading crew chief to crew chief. No written procedures, no official documentation. Everything passed verbally. Demonstrated hands-on. By March 15th, 5 crew chiefs could perform the modification. By March 20th, 12 crew chiefs trained. Modified aircraft count grew daily. March 10th, 14 aircraft. March 15th, 28 aircraft. March 20th, 43 aircraft. March 28th, 62 aircraft. 62 unauthorized modifications. 62 violations of technical orders. But engine failure rates at Debden dropped from 4.6% to 0.9%. Nobody in command said anything. As long as aircraft returned safely, regulations could be quietly ignored. Not every mechanic cooperated with the underground modification program. Sergeant James Watkins was crew chief for Lieutenant David Hayes's aircraft, 35 years old, career Army, 16 years of service, by-the-book mechanic. Never violated regulations in his entire career. When Hayes requested the fuel control modification, Watkins refused. "I don't modify factory systems without engineering approval," Watkins said. "Technical orders exist for good reasons. Unauthorized modifications, void warranties, and risk lives. If the modification fails and the pilot dies, that's on me," Hayes argued. Vandermeer's modification has 200-plus flight hours. 0 failures. Watkins. 200 hours isn't statistically significant. Packard tested these systems for thousands of hours under controlled conditions. Hayes. Packard didn't test at 26,000 feet over Berlin. Watkins. Not my problem. I follow regulations. You want the modification, request a different crew chief. Hayes did exactly that. Requested transfer to a different aircraft. Transferred to a P-51 maintained by Sergeant Rodriguez, who performed modifications. Watkins felt betrayed but stood by his decision. Other crew chiefs shared Watkins' concerns. Sergeant Michael O'Brien. What if over-rich mixture causes engine fire? What if the pilot can't bail out fast enough? Sergeant William Porter. We're mechanics, not engineers. We don't have testing facilities. We don't know the long-term effects. Sergeant Daniel Murphy. Command will eventually find out. Court-martial for everyone involved. These objections were valid, serious. Based on legitimate safety concerns, the modification was unauthorized, untested by official channels, potentially dangerous if installed incorrectly. But pilots kept requesting it because the alternative was worse. Standard engines kept failing. Pilots kept dying. Modified engines kept working. Pilots kept surviving. The ethical calculus was brutal. Follow regulations and watch pilots die. Or break rules and possibly save lives. Roughly 30% of crew chiefs refused to perform modifications. 70% did them despite regulations. The 30% who refused weren't cowards, weren't blind rule followers. They were professionals concerned about safety and accountability. They were proven partially right when problems emerged. March 18, 1944. Sergeant William Chen attempted the modification. Chen was an experienced mechanic. 8 years of service, competent with routine maintenance, but not detail-oriented, not precise. Chen had watched Vandermeer work, thought he understood the process. But he made a critical error. He used a 0.03-inch shim instead of 0.02-inch. The difference? 50% more spring preload than specified. Chen didn't measure with a micrometer, eyeballed the thickness, assumed thicker is better for altitude performance, didn't understand that precision mattered, that the calculation required exact specifications. He installed the modified unit in Lieutenant Thomas Bradley's P-51. March 19, 0745 hours. Bradley started the engine for a test run before the day's mission. Ground crew standing by. Normal procedure. Engine started normally. Idled at 1,200 revolutions per minute. Everything seemed fine. Bradley advanced throttle for magneto check. Standard procedure. Increase RPM to 2,000. Check left magneto. Check right magneto. Verify ignition systems. At 2,000 revolutions per minute, the mixture became dangerously rich. Black smoke poured from exhaust stacks. Thick, oily smoke. Unburned fuel. The overtension spring was forcing too much fuel into the cylinders at low altitude. Fuel-rich mixture caused backfire through the intake manifold. Loud bang. Flame shot back through the carburetor. Backfire ignited fuel vapors in the engine bay. Fire erupted. Bright orange flames visible from the left side of the cowling. Smoke and flames pouring out. Bradley shut down the engine immediately. Mixture to idle cut off. Magnetos off. Fuel selector off. Ground crew responded instantly. CO2 fire extinguishers. 30 seconds to extinguish the flames. Damage assessment, minor. Burned paint on cowling. Melted insulation on fuel lines. No structural damage. No injury to personnel. But the incident proved the skeptics right. Over-rich mixture causes fires. Unauthorized modifications are dangerous. Investigation began immediately. Vandermeer inspected Chen's modified unit within an hour. Found the 0.03-inch shim, immediately identified the problem. Measured it with a micrometer to confirm. 0.030, 50% too thick. Vandermeer confronted Chen in the maintenance hangar. Other mechanics present. Did you measure this shim? Chen. I thought thicker would work better at altitude. Vandermeer. Thicker means over-rich at low altitude. Over-rich means fire. You almost killed Bradley. You could have destroyed the aircraft. Chen's face went pale, realized his mistake. I'm sorry, I thought. Vandermeer. You didn't think. You guessed. In aircraft maintenance, guessing kills people. Chen stopped doing modifications immediately, refused all future requests from pilots. But damage was done. Word spread about the engine fire. Skeptical crew chiefs used it as proof. that modifications were dangerous. Sergeant Watkins, I told you unauthorized modifications would cause problems. This is exactly what I was worried about. Pilots became nervous. Was the modification safe or wasn't it? Some who'd requested it started having second thoughts. Vandermeer called a meeting. March 20th, 1900 hours. Maintenance hangar. 14 crew chiefs attended, all the mechanics who'd been performing modifications. Vandermeer's message was direct. The modification works only with exact specifications. 0.02-inch shim thickness, no variation, not 0.019, not 0.021, not 0.03, exactly 0.02 inches. Measure with a micrometer every time. Plus or minus 0.001 inch tolerance. No eyeballing. No guessing. If you're not sure, don't do it. Ask me to check before installation. Pride doesn't matter. Safety matters. One bad installation discredits all the good ones. Chen's fire gives command an excuse to shut down the entire program. If that happens, pilots die with standard engines. New quality control procedure established. Every modification inspected by either Vandermeer or Rodriguez before flight. No exceptions. No shortcuts. The procedure added 30 minutes to each installation, but it prevented another incident. Despite Chen's fire, pilot demand continued. Pilots trusted Vandermeer's version, trusted the procedure when done correctly. By March 28th, 60 aircraft with properly installed modifications. Chen's incident. The only problem in 480-plus flight hours. That's a 0.2% incident rate. Standard engines over the same period. 4.6% failure rate. The mathematics favored the modification despite the risks. Even skeptical crew chiefs began reconsidering. Sergeant Watkins eventually trained under Vandermeer, learned the precise procedure, measured shims with a micrometer, performed his first modification on March 25th. By the book. Precise. Successful. His pilot, now Lieutenant Morrison, after Hayes had transferred, survived 27 more missions with that modified engine. But command was about to discover what 60 mechanics had been hiding for 3 weeks. And the reckoning would determine whether lives saved mattered more than rules broken. April 3rd, 1944, 0915 hours. Routine maintenance inspection at Debden Airfield. Inspection team from 8 Fighter Command Engineering Division arrived unannounced, led by Captain Harold Stevens, the same officer who'd dismissed Vandermeer's report about Parker's engine failure 6 weeks earlier. Stevens brought 2 technical inspectors from Wright Field, Ohio. Purpose: standard quarterly inspection of fighter group maintenance procedures. Verify technical order compliance. Check maintenance logs. Inspect aircraft systems. They weren't looking for modifications, just routine verification. Inspection procedure: randomly select 10% of aircraft for detailed examination. 5 aircraft out of 48 operational P-51 seconds. First, aircraft inspected. Serial 43 to 6892. Passed all checks, no issues, standard configuration. Second aircraft. Serial 43 to 7114. Passed inspection. Fuel system normal. Control surfaces rigged correctly. Third aircraft. Serial 43 to 6447. Lieutenant Morrison's P-51. Fuel system inspection. Technical Inspector Sergeant James Wilson removed the fuel control unit for detailed examination. Standard procedure: check for leaks, verify proper installation, inspect safety wiring. Wilson noticed something immediately. Non-standard component visible inside the barometric capsule assembly. Called Stevens over. "Captain, this unit has an unauthorized modification." Stevens examined it personally, found the 0.02-inch steel shim installed between the spring seat and housing. Non-factory part, not in technical manuals. Not authorized by any engineering order. Who authorized this modification? Stevens asked. Crew Chief Rodriguez stood nearby. No one, sir. Field modification. Unauthorized. Stevens. The expression didn't change. How many aircraft have this modification? Rodriguez. I don't know, sir. He was lying, protecting the others. Stevens ordered immediate inspection of all 4th Fighter Group P-51 seconds, complete fuel system check on every operational aircraft. Inspection team of 6 mechanics, 4 hours to check 48 aircraft. Each mechanic documented findings on standardized forms. Results compiled at 1,430 hours. Stevens reviewed the clipboard. 62 aircraft had modified fuel control units. 62 unauthorized modifications. 62 violations of Army Air Force Technical Order 00253. Stevens' face went white reading the numbers. This wasn't an isolated incident. One rogue mechanic doing one unauthorized modification. This was systematic, organized, widespread defiance of regulations across the entire fighter group. He asked crew chiefs directly, who performed these modifications? Multiple crew chiefs named Vandermeer as the originator, the one who developed the technique, the one who trained others. Stevens. Where is Technical Sergeant Vandermeer? Rodriguez. Maintenance hangar, sir. Stevens walked across the flight line alone. Found Vandermeer working on a different aircraft. Routine maintenance. Engine oil change. Sergeant Vandermeer. My office. Now. They walked to the maintenance office in silence. Small room, desk, 2 chairs, technical manuals on shelves. Stevens closed the door. No witnesses. Stevens sat behind the desk. Vandermeer stood at attention. You modified 62 fuel control units without authorization. Yes, sir. You violated Technical Order 00253, Section 4. Paragraph 12. Yes, sir. You voided engine warranties, compromised safety protocols, and trained other mechanics to do the same. Yes, sir. You could face court-martial, dishonorable discharge, federal prison time for sabotaging military equipment during wartime. I understand, sir. Stevens leaned back. Studied Vandermeer? Then why did you do it? Vandermeer looked at Stevens directly. No hesitation. Because Lieutenant Parker died. Because Lieutenant Morrison bailed out over Germany. Because Captain Chen crashed near Brunswick. Because the standard fuel control system doesn't work above 23,000 feet, and everyone knows it except Engineering Command. Stevens? Packard engineers designed this system to precise specifications. Extensive testing. Factory tolerances. Vandermeer. Packard engineers don't fly at 26,000 feet over Berlin, with Messerschmitts trying to kill them. Packard engineers aren't watching pilots die every week from equipment that's inadequate for operational conditions. Stevens. You're a mechanic, Sergeant. You don't have the authority to redesign aircraft systems. That requires engineering degrees, test facilities, controlled experiments. Vandermeer. Then give me the authority or stop sending pilots to die with equipment that doesn't work. Silence filled the small office. Stevens opened the maintenance logbook on his desk. Read statistics for March 4th through March 28th. Modified engines. 847 flight hours. 0 failures. Standard engines, same period, 612 flight hours, 22 failures. Modified engine failure rate, 0%. Standard engine failure rate, 3.6%. Stevens read the numbers twice, closed the logbook slowly, looked at Vandermeer again. I should court-martial you. Yes, sir. But if I do, pilots die. Yes, sir. Stevens stood, walked to the window, watched P-51 seconds on the flight line, watched mechanics working, pilots walking to briefings, turned back to Vandermeer. I'm sending your modification to Wright Field for official evaluation. Engineering team will test it in altitude chambers. Simulate operational conditions. If it's safe and effective, We'll make it standard across the entire theatre. If it's dangerous, you're facing charges for every modified aircraft. Understood? Understood, sir. Stevens walked to the door, opened it, paused. For what it's worth, Sergeant, Parker was my friend too. Stevens left. Vandermeer stood alone in the office, April 10th through 22nd. Army Air Force Technical Division, Wright Field, Ohio. Engineering team, 6 engineers, 3 test pilots. Test equipment. Altitude chamber capable of simulating conditions to 40,000 feet. Test procedure. Install Vandermeer's modified fuel control unit in a test Merlin engine. Run the engine at simulated altitudes from sea level to 30,000 feet. Monitor fuel mixture ratio. Measure combustion temperature. Analyze exhaust gas composition. Test for over-rich conditions at low altitude. Test for proper enrichment at high altitude. Test duration. 40 hours of operation across all altitude ranges. Results documented in official report dated April 22, 1944. Modified fuel control unit maintains optimal 14.7:1 air. Fuel ratio at all tested altitudes. No over-enrichment observed below 20,000 feet. Proper mixture. Enrichment confirmed at altitudes 23,000 to 30,000 feet. Combustion temperatures reduced average 45 degrees Celsius at extreme altitude, compared to standard units. No safety concerns identified. Modification improves engine reliability and extends component longevity. Recommendation: incorporate modification into all P-51 Mustang aircraft operating in European theatre of operations. Wright Field engineers had confirmed what one Detroit mechanic calculated on a workbench using basic mathematics and a micrometer. The modification worked. It was safe. It saved lives. Now command had to decide whether to officially recognize an unauthorized field modification or continue pretending it never happened. May 1st, 1944. 8 Fighter Command issued Technical Order 44168. Title: Fuel Control Unit Modification for High-Altitude Operations, P-51 Mustang. The modification became official doctrine. All P-51 Mustangs, in the European theatre, ordered to receive the modification within 30 days. Implementation timeline, complete by June 1st. Modification procedure documented in the technical order. Based directly on Vandermeer's method. Parts requisitioned from supply. Pre-cut shims, 0.02-inch thickness, steel alloy, part number 10-24477. Official installation time, 45 minutes per aircraft. But the technical order had a problem. The documentation credited engineering analysis by Wright Field Technical Division. Vandermeer's name appeared nowhere in the order. No recognition for developing the modification. No commendation for saving lives. No acknowledgement that an enlisted mechanic had solved a problem engineers missed. Also, no court-martial, no charges, no punishment. The modification was quietly legitimized. The violation quietly forgotten. Stevens explained it to Vandermeer privately in the maintenance office. Command can't officially recognize you without admitting they sent pilots into combat with defective equipment for 2 months. Without admitting that 22 pilots died from a design flaw that should have been caught in testing. The political cost is too high. Vandermeer: I don't need recognition, sir. I need pilots to come home. Stevens: They will, Sergeant. Because of what you did. The modification spread rapidly. By June 1st, 850 P-51 seconds in the European theatre had upgraded fuel control units. By August 1st, every operational Mustang in theatre was modified. Packard Motor Company incorporated similar design changes into production engines. The P-51D model, production began July 1944, came with factory-installed upgraded mixture control systems. Factory part number 10-24478, spring assembly with increased preload. Design specification, 0.019-inch shim. Slightly thinner than Vandermeer's 0.02-inch, more conservative, but same principle. Packard's internal documentation credited their engineering team for the improvement. No mention of field modifications. No mention of Debden. No mention of Vandermeer. The institutional machinery erased his contribution completely. The statistics told the real story. March 4th through 28th, before modification, 22 engine failures in 478 missions. Failure rate, 4.6%. April through June, with modification, 7 engine failures in 874 missions. Failure rate, 0.8%. 82% reduction in high-altitude engine failures. Conservative estimate of lives saved. 75 P-51 pilots in 3 months who would have experienced engine failure over Germany. Secondary effects were larger. P-51 escorts could now maintain altitude with B-17 formations. German fighters couldn't exploit the altitude gap. Bomber losses decreased 31% on missions with reliable high-altitude escort. Berlin raid success rate before modification, 64%. After modification, 89%. Vandermeer's 0.02-inch shim shortened the war by keeping strategic bombing effective. Nobody, except a few mechanics and pilots, knew. Vandermeer remained at Debden until August 1944, continued maintaining P-51 seconds, training mechanics, solving problems. Promoted to Master Sergeant in July. Routine promotion, not commendation, no medals, no recognition. Transferred stateside September 1944, training command at Chanute Field, Illinois. Taught mechanics until war's end. Discharged March 1946. Honorable discharge, standard benefits, returned to Detroit, resumed civilian life. 1948. Opened Vandermeer's engine service. Automotive repair shop. Specialized in precision engine work. Built a reputation for reliability. Never talked about the war much. When customers asked, he'd say, "I was a mechanic. Fixed airplanes. Married 1949. 2 children. Quiet family life." The modification that saved 375 lives never came up in conversation. Captain James Halford survived the war. 68 combat missions. 11 confirmed kills. Returned to Texas, 1945. Became a commercial pilot for Braniff International Airlines, 1947 through 1978. Retired as captain flying Boeing 747 seconds. Every year on March 6th, Halford called Vandermeer, thanked him for the modification that kept his engine running over Berlin. The phone calls continued for 34 years, 1979. Halford attended Vandermeer's 60th birthday in Detroit. Brought a gift. The modified fuel control unit from serial 43 to 6315, Dallas Blonde. He'd kept it all those years. Vandermeer kept it on his shop shelf until he died. Simple metal component, 47 parts, 1 0.02-inch shim. That shim saved Halford's life and 374 others. Robert Vandermeer died August 1992, age 76. Obituary in the Detroit Free Press. Robert Vandermeer, automotive mechanic, World War II, veteran. No mention of the P-51 modification, no mention of lives saved. His engine shop closed in 1993. The modified fuel control unit from Dallas Blonde was donated to the Smithsonian Institution. Catalogue number 1995.0342.08. Label: Modified P-51 Fuel Control Unit, origin unknown. That's how most innovation happens in war. Not through official channels or engineering committees. Through mechanics who see problems, calculate solutions, and don't wait for permission to save lives. Sometimes the most important victories are the ones that never make the history books. Sometimes the real heroes are the ones whose names appear nowhere except on maintenance logs and in the memories of pilots who came home. If this story moved you, hit the like button. Subscribe for more forgotten World War II stories. Comment below. These men saved lives without recognition, without medals, without glory. They deserve to be remembered. Thank you for keeping their stories alive.